Higher order derivatives. Repeated differentiation. Suppose we have a function f, and we define a dependent variable y equal to f of an independent variable x. The derivative, or first derivative, is dy dx, or f prime of x. We define the second derivative of f to be the derivative of the first derivative. In shorter Leibniz notation, this looks like d squared y over dx squared, and we denote it also as f double prime of x. The third derivative is, of course, the derivative of the second derivative, or f triple prime of x. The fourth derivative is the derivative of the third derivative, and by the time we get to the fourth derivative, we often switch from prime notation to a type of superscript notation, such as what you see here. Now, in general, we can talk about the nth derivative of y with respect to x, or the nth derivative of f. Example: suppose y equals x cubed minus x squared. Then, using the power rule, the first derivative is 3x squared minus 2x, and the second derivative is the derivative of the first derivative, or 6x minus 2. So the third derivative is the constant function 6, and the fourth derivative is the constant function 0. In fact, all higher order derivatives are also 0. This is typical of a polynomial. For an nth degree polynomial, all derivatives of order n plus 1 or higher will be 0. Example: let f of t equal sine of 2t. The derivative is cosine of 2t times the derivative of 2t by the chain rule. The second derivative is minus sine of 2t times another 2 to give us minus 4 sine of 2t. The third derivative is minus 8 cosine of 2t. Each time we differentiate, we pick up another factor of 2. The fourth derivative is 16 sine of 2t. Another example: let w of x equal x to the 1/2 power of the square root of x. Then the first derivative w prime of x is equal to 1/2 x to the minus 1/2 by the power rule, or 1 over 2 times the square root of x. The second derivative, again using the power rule, is minus 1/4 x to the minus 3/2, or minus 1 over 4 times the square root of x cubed. The third derivative, w triple prime, is 3/8 x to the minus 5/2, or 3 over 8 times the square root of x to the 5th. Graphical interpretation of the first and second derivatives. F of x is increasing when f prime of x is positive and decreasing when f prime of x is negative. Here's the graph of a function f on an interval on which f of x is increasing. Notice that the slope of the tangent line is always positive over that interval. Here's the graph of another function on an interval on which it's increasing. Again, notice that the slope of the tangent line is always positive, and so f prime of x is always positive on that interval. Here's the graph of a function f on an interval on which the function is decreasing. Notice the tangent line always has a negative slope. Here's the graph of another function f on an interval on which it's decreasing. So in each of those pictures, f prime of x is negative on the interval. The tangent line always has negative slope, corresponding to decreasing function values. Now, just as f is increasing when f prime is positive and decreasing when f prime is negative, we can say that f prime of x is increasing when f double prime is positive and decreasing when f double prime of x is negative. Here's the graph of a function on an interval on which f double prime is positive, or f prime of x is increasing. Now let's think about why that's so. Close to the left endpoint of the interval, our graph has a negative slope. Now, as we move from left to right along the graph, the slope is increasing. Here, the negative slope is getting smaller. Finally, we get to a point here where the slope is 0. And then since the slope is increasing, it becomes positive, and that part of the curve is getting steeper. So in this picture, f double prime of x is positive, corresponding to an always increasing slope, and the shape of the graph is said to be concave up, or convex. Let's look at the opposite situation. Near the left endpoint of the interval, the slope is positive and fairly large. As we move from left to right, that positive slope decreases, eventually becomes 0, and continues to decrease, becoming negative, and continues to decrease as the curve gets steeper with negative slope. So here f double prime of x is always negative, corresponding to an always decreasing slope, and a graph that is said to be concave down, or simply concave. Example. Suppose we have a function whose graph is shown here. Starting near the left end of the interval, we notice that the slope is positive there, and as we move from left to right, that positive slope is decreasing, eventually becoming 0 here, and then becoming negative until we reach a point near the middle where the slope will begin increasing again. So there's a value of x where, to the left, the slope of the graph is decreasing, the graph is concave down, and over the corresponding interval, f double prime of x is negative. Now, when we cross over that point in the middle of the interval, our slope starts to increase, eventually becoming positive as the graph gets steeper and steeper. So on that part of the graph, our slope is increasing, and the graph is concave up, and so over the corresponding interval, f double prime of x is positive. The point where the concavity changes from down to up is called an inflection point. In this case, it's a point where f double prime changes from negative to positive. This graph is actually the graph of the function f of x equals x cubed minus x plus 2, whose first derivative is 3x squared minus 1. Let's overlay the graph of the first derivative onto our picture. Notice that the x-intercepts on the graph of the first derivative correspond to the points on the graph of f where the slope is 0, and that the values of f prime are negative where the slope of the graph of f is negative, and the values of f prime are positive where the slope of the graph of f is positive. Now let's look at the second derivative. It's 6x, whose graph is a straight line through the origin. Notice f double prime has positive values when x is greater than 0, corresponding to the concave up section of the graph, and the values of f double prime are negative when x is less than 0, corresponding to the concave down section of the graph of f. Local approximation by polynomials. Linear approximation. We define a linear function L sub a of x equal to f of a plus f prime of a times x minus a. This is the linear approximation of f at x equal to a. Let's notice that the derivative of L sub a is simply equal to the derivative of f of a with respect to x, which is 0, since that's constant, plus the derivative of f prime of a times x minus a, which is just the constant f prime of a. L sub a is the linear function that has the same value as f at a, as well as the same derivative as f at a. Here's a typical picture. The linear approximation's graph is nothing but the tangent line at x equals a, and L sub a is in fact the unique linear function whose value and first derivative agree with f at x equals a. Now, quadratic approximation. We define q sub a of x to be f of a plus f prime of a times x minus a, which is just the linear approximation at a, plus a quadratic term 1/2 f double prime of a times x minus a squared. Now let's look at the derivatives of this function. Q prime of a of x is equal to the derivative of f of a, which is 0, plus the derivative of f prime of a times x minus a, which is the constant f prime of a, plus the derivative of the quadratic term, which by the power rule will be f double prime of a times x minus a to the first power. The second derivative then is the derivative of f prime of a, which is 0, plus the derivative of f double prime of a times x minus a, which is just the coefficient f double prime of a. So now let's notice that the function q of a has the same value as f does at a. The value of its derivative at a is the same as f prime of a, and the value of its second derivative at a is also the same as f double prime of a. So let's look at a picture here. Same graph as above. This is what the graph of the quadratic approximation looks like. This is the graph of the unique quadratic polynomial whose value, first derivative, and second derivative all agree with f at x equals a. Example. Let's find the linear and quadratic approximations to f of x equals 1 over x at x equals 1. We begin by taking derivatives and evaluating them at 1. F of x is 1 over x, or x to the minus 1 power, so its derivative is minus x to the minus 2 power, or minus 1 over x squared. So its second derivative ends up being 2 times x to the minus 3 power, or 2 over x cubed. Now f of 1 is equal to 1, f prime of 1 is minus 1, and f double prime of 1 is 2. So the linear approximation at 1, L sub 1 of x, is equal to f of 1, which is 1, plus f prime of 1, or negative 1, times x minus 1, which simplifies to 2 minus x. The quadratic approximation is the same as the linear approximation in its first two terms, plus the quadratic term 1/2 of f double prime of 1, or 2, times x minus 1 squared, or 2 minus x plus x minus 1 squared. Let's look at the graph of what we've found here. Here's the graph of 1 over x, and you see the point 1, 1. The linear approximation's graph is just the tangent line there. The graph of the quadratic approximation is the parabola that best fits the curve there. Let's magnify the graph a little bit near the point 1, 1. Notice that the graph of the quadratic approximation, the blue graph here, follows the graph of 1 over x, the black curve, considerably better than the straight line graph of the linear approximation. To further illustrate this, let's use the linear and the quadratic approximations we've found to approximate the value of f at 1.1, or in other words, to approximate the number 1 over 1.1, or 10/11. The linear approximation evaluated at 1.1 is 2 minus 1.1, or 0.9. The quadratic approximation at 1.1 is 2 minus 1.1 plus 0.1 squared, or 0.91. Now for comparison, let's look at the exact value of 1 over 1.1. It has a repeating decimal expansion, 0.90909, and so on. So we see that the linear approximation gives us 1 decimal place of accuracy, while the quadratic approximation gives us 2 decimal places of accuracy, in the sense that the exact value of the function rounded to 2 decimal places is precisely the same as the quadratic approximation rounded to 2 decimal places. Quadratic approximation and concavity. Let's recall our formula for the quadratic approximation. F of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared. Now the coefficient of x squared here is 1/2 f double prime of a. So the graph of this quadratic function is a parabola that opens upward if f double prime of a is positive and opens downward if f double prime of a is negative. For example, consider this graph. Here we see the quadratic approximation at a point where the graph is concave down. And here we see the quadratic approximation at a point where the graph is concave up. Next, let's look at an animation that shows the quadratic approximations moving along that same curve from left to right. The blue line here is the graph of the second derivative. Cubic approximation. This is as high as we'll go. Our purpose here is simply to indicate how higher degree approximations can be constructed. The cubic approximation to f at x equals a, we denote by c sub a of x, is a cubic polynomial whose first three terms are exactly the same as the quadratic approximation of f at x equals a, plus a cubic term of the form 1/6 times f triple prime of a times x minus a cubed. Now let's look at the first three derivatives of this function. C sub a prime of x is equal to the derivative of f of a, which is 0, plus the derivative of the second term, which is f prime of a, plus the derivative of the third term, f double prime of a times x minus a to the first power, plus the derivative of the cubic term, which is 1/2 of f triple prime of a times x minus a squared. Now the second derivative is 0 plus the derivative of f prime of a, which is 0 since that's constant, plus the derivative of the third term, which is f double prime of a, plus the derivative of the last term, f triple prime of a times x minus a to the first power. And the third derivative, c sub a triple prime of x, is 0 plus the derivative of the constant f double prime of a, which is 0, plus the derivative of the last term, which is the constant f triple prime of a. So we observe that the value of c sub a prime at a is the same as the value of f prime at a. The value of c sub a double prime at a is the same as the value of f double prime at a. The value of c sub a triple prime at a is the same as the value of f triple prime at a. So this is the unique cubic polynomial whose value, as well as the values of its first three derivatives, agree with corresponding values of f at x equals a. For example, let's look at f of x equals 1 over x again at x equals 1. We've calculated f prime of x equals minus 1 over x squared, f double prime of x equals 2 over x cubed, and now f triple prime is minus 6 times x to the minus 4 power, or minus 6 over x to the fourth. So the cubic approximation at 1, c sub 1 of x, is equal to 1 plus the value of f prime at 1, which is negative 1, times x minus 1, plus 1/2 times the value of f double prime at 1, which is 2, times x minus 1 squared, plus 1/6 times the value of f triple prime at 1, which is negative 6, times x minus 1 cubed. So we have 2 minus x plus x minus 1 squared minus x minus 1 cubed. If we expand and simplify, we find that this can be written as minus x cubed plus 4x squared minus 6x plus 4. So let's look at the graph of y equals 1 over x again at x equals 1. Recall that the linear approximations graph is simply the tangent line. Here's the graph of the quadratic approximation. And now let's look at the graph of the cubic approximation. Notice that it follows the curve very closely near the point 1, 1.